not recorded for all time. Okay. Yeah, right. Okay, so a graph of an equation. So here's some possible answers. Cannot be used to determine solutions for an equation. Is that true or false? False. That's exactly what you use a graph for. Graph has no practical application. A graph shows only one solution for an equation. False. It represents all possible solutions for the equation, or provides very precise answers for solutions. To some extent. Graphs by themselves aren't going to give you very precise, because it's all in how precise is everything laid out. Like this graph, that's not precise, because the measurements, the marks are not the same. If you're trying to graph, things are going to be off. Even when you have your calculator or computers do that, they're going to be off just a little bit, because there comes to a certain point where they have to round. And then you're eyeballing what's actually going on. So if you want precision, you're not necessarily going to use a graph. But if you want to be able to see the trends, to get a general idea of what it should be, and sometimes, yes, they will give you the exact answer. But sometimes it's a little bit harder to get that. Does that make sense with graphs? For that. When you have an equation for a line, or for a slope, or anything like that, we're going to use the standard form, y equals mx plus b. Okay? Did come back. Okay? What is the m? The slope. What does that mean? Rise over run. How steep it is, how flat it is, what direction it's going. If you have a positive slope, how's your graph going to look? Left to right, going up. If it's a negative slope, the opposite. Left to right, going down. What are the different parts? So we got the m. What's the x? That's your x coordinate. Your y is your y coordinate. B is the intercept where it crosses the y axis. If I gave you the points, let's see, where did they go? If I gave you the point 3, 2, what does that mean? Yep. 3, 2 is that point right there. Versus 2, 3, which is going to be here to here. And it's listed as x over y, or x comma y. Basically, if we wanted to take a formula and move it into slope-intercept form, let's say I was given 2x plus 4y equals 3. How do I convert that into slope-intercept form? Get y by itself, which is just what we were doing with these ones. So 4y minus, or equals negative 2x plus 3. Y is equal to negative 1/2 x plus 3/4. Let's see. The other one is you have an equation. So we'll go with this guy. We have y is equal to negative 1/2 x plus 3/4. I want to know what is my y coordinate at x equals 3. Where am I going to plot that if all I'm given is a coordinate and my slope? Well, where's that point? Is it going to be 3, 0? Negative 5/4. Because you plug in x for your value and you solve for the y coordinate. Again, you have two variables, you're given one of them, you can solve for the other one. So if you were looking for what is my y value when my x value is 3, is going to do that. Your coordinate then is going to be 3 and look like that. Does that make sense, Zach? Okay. So the idea is you're given an equation for a line, and then you want to find out where this point is going to be where your x is equal to 3. So you're going to plug your 3 value in for here, and then solve down for your y value. This point, it's just algebra. That's all we're doing. Okay, if I wanted to know where does this cross the y-axis, where's it cross the y-axis at? 3/4. Because if it's crossing the y-axis, our x value is 0. Plug the 0 in for there and solve down for y, which is what we just did on that one. Okay, that's as far as we're going to go in depth as far as graphing goes. We'll have a little bit more when we start getting into some of the AC. We're going to have more coordinates that we're going to post or plot. Yep. And it's about finding locations on the graph. So that's why we're talking about this now, is getting you guys prepared for that. Okay. Last thing that we're going to talk about today, and then we'll turn it over for questions, is simultaneous equations. Yes. Okay. Simultaneous equations is a system of equations that have the same variables in them. In these equations, there has to be one equation for every variable that you need to find. So if you're looking for 2 variables, you have to have 2 equations to solve from. If you have 3 unknowns in your equations, you have to have 3 different equations to solve for it. Then what you're going to do is then you solve them using systems, using arrays, things like that. We're just going to go through one method of how to do it. The idea behind this is you're solving multiple things at the same time. That's what we're doing. And so one of the things we'll use this for is we can use simultaneous equations to solve the bridge circuit. We can use the bridge, solve for resistor 3, that middle part, and then we use simultaneous equations to solve for everything else. Let's see. So all the variables are dependent on each other, and we have to use them together to determine the proper outcome. That's kind of what we were doing with the universal shunt meter. We had multiple equations that we were using built into everything, but we were getting them at different points instead of just plugging them all in and solving them all at once, which we could have. All right. So with that, what we're going to have is, so for example, we have these equations. We have 2x minus 2y is equal to 10. We have 3x plus y is equal to 7. So for an example of where these would come from, these are 2 Kirchhoff's voltage loops. Okay? We have a voltage and a current, a voltage and a current. We're trying to solve for one current and solving for another opposing current. This is what we're going to be doing next week when we talk about mesh analysis. Okay, so the first thing to solve for these guys is, like I said, we have to make sure we have the correct number of equations. We have 2 variables, we have 2 equations. Now we need to pick one of these variables that we want to eliminate from both of these guys at the same time. And then basically, what do we need to do to these equations to get them so we can eliminate them? And then we'll go through and solve for the variables. So in this case, we have 2x and 2y. Which variable do we want to get rid of between these 2 equations? Okay, let's get rid of the x. So what do we need to do to be able to, when we add these guys together and combine them together to get rid of the x? What's the first thing we need to have? Like terms. We need to have the coefficients to be the same. We need to have them opposite polarity. So to get rid of the x's, what is the least common multiple between 2x and 3x? 6x. Okay? So we need to get these guys to one of them as positive 6x and one of them as a negative 6x. So what do we need to do to this top one to get positive or negative 6x? We just have to choose. Times 3. So that means if we're multiplying this one by 3, this one we have to multiply by a negative 2. Because we want same magnitude, opposite polarities. So then, if we multiply the entire equation by the same value, we're not going to change how the equation works. So we end up with 6x minus 6y is equal to 30. So I distribute that 3 all the way through. And then I end up with a negative 6x minus 2y is equal to negative 14. So then, once we have that, now we get to combine everything together. So we're just going to add these two guys together. So those guys are going to cancel. We have a negative 6y minus a 2y gives us negative 8y is equal to 16. And then at this point, we just solve for y. Divide both sides by negative 8. Y is equal to negative 2. Yes?
Couldn't you choose one of the first two and solve for y and then plug it in?
Can I just subtract 3x on both sides?
Yeah, you could do that as well. You could. That would save steps.
But it's still the same process.
So you end up with the negative 2. Then, what you're going to do is you're going to take this value and you're going to plug it back into one of your two original equations to solve for the other variable. So we have 2x minus 2 times a negative 2 is equal to 10. 2x plus 4 is equal to 10. 2x is equal to 6. X is equal to 3. Then we just double check our answers. We could pick one of the equations, doesn't matter, and we plug in both those variables and make sure we get the answer that we're supposed to. So 10 on both sides. So if we did 2x plus times 3 minus 2 times a negative 2. So we're going to get 6 plus 4 equals 10. So we're good. Does that make sense? Let's look at another example. So we've got x over 2 plus y over 2 equals 6. And x over 4 plus y over 2 equals 3. So now we need to get one of these equations, or we need to get these equations, we need to remove one of the variables. So which variable do we want to get rid of? Why? Yeah. So one thing we can look at is, do we have similar variables that we could get rid of so we don't have to change both equations? So if we want to get rid of the y, what do we need to do to this bottom equation? Multiply it by -1. So we get a negative x over 4 minus y over 2 is equal to -3. So we've changed this guy. We'll add these together. Those are going to fall out. So we get an x over 2 minus an x over 4 is equal to 9. Or sorry, 3. I did a double negative is what I did. I was. It's true. So if we have x over 2 minus x over 4, yeah. So we have a half, think of it this way, we have a half minus a quarter. What do we have left? A quarter. So here, we need to make these guys equal. So we're going to multiply this top and bottom by 2 because we want to get this to equal 4. So we have 2x over 4 minus an x over 4. So now we can just do this math straight across. 2x minus x is x over 4. So we have x over 4 is equal to 3. Then we need to isolate the x and get it by itself. So we multiply both sides by 4. Those will cancel. X equals 12. Then we plug that back into one of our original equations and solve for the other variable. Just like what we were doing, like I said, with the universal shunt meter. So we have 12 divided by 2 plus y over 2 is equal to 6. So 12 divided by 2 is 6 plus y over 2 equals 6. Because 6 minus 6 is 0. Anything multiplied by 0 is 0. Anything divided by 0 is? Can't divide by 0. So that's another check too. Is if you come up to one of these, look at the answers. If there's an option for does not exist, then you're dividing by 0. If there's not an answer in there that says does not exist, you're probably not dividing by 0 and you made a mistake somewhere. Do you guys know that Chuck Norris can divide by 0? That's true. Chuck Norris said so, so it has to be true, right? Huh? Okay, let me grab. Any questions so far about the simultaneous equations? Okay. Let's go back to our bridge.
I want to have some questions if this is what we're going to move on to.
Just like went from 100 down to 1 and back to 100 again. So I'm like,
Well, we got to give you guys brains a chance to recoup.
I'm gonna need at least the 84-hour wait period.
You can see what we zoomed out at.
Yeah, it's true. All right, so we've got 41 volts. We've got 2K, 6.2K, 1.8K, 3K, and 5.1K. And then the voltage we did get across R3 was 5503. 21,446, 19,554, and 25,066. Come on.
Bro, you need to stick of your trap. It's sick of your trap.
It is.
Oh.
It doesn't want to play. Okay. So we have 41 volts. We've got 2 kiloohms here. We have 6.2 kiloohms here. We've got 1.8K here. We have 3K here. And we have 5.1K here. So going through this, we Thevenized V3 already, and we got 5.503 volts in this polarity. So what we need to do is we need to figure out what equations are we going to use to be able to use simultaneous equations to solve for this. So it's going to take a step farther than what we did. So we're combining Thevenin and simultaneous equations. So one of the things we'll have is we need to do 2 separate voltage loops across this guy. So one of the things we want to incorporate is a value that we have here. So we can go this way. Another one we can do what? Yeah, so this is where we get into the simultaneous equation part. So there's 2 loops. One loop gives us the current through R2 times R2, the current through R3 times R3, and these voltages all have to equal 0. So for example, with the purple loop, we have a negative 41 volts. We come across, we have plus IR2 times 2K plus the 5.503 plus the IR4 times 3K equals 0. There's our Kirchhoff loop. How many unknowns do we have in that guy? Nope, it comes across this way. Back up to here. The pink loop does.
Oh, I see.
And then pink does the negative 41 volts, the plus IR. Oh, this should be IR1, not IR2. Damn it. 1. Yes. Okay. So there, which variables do we have? We've got IR1 and IR4, IR2 and IR5, which we can then solve for the voltages. So far, we don't have 2 equations yet that we can use with 2 of the same variables. Yes?
Can you remind me, how you decided to make, the 1.8K or the 5.5 volts, adding it or subtracting it?
Okay. So when we came in, we knew that this guy's voltage was established as this.
Is it always established as well?
Depends on what we come up with when we Thevenize it. Because we're looking at our VAB, So here we had a positive VAB. So we knew that the voltage across this guy was going to be positive to negative. If we get a negative VAB, it's going to be positive over here and negative over here because we measure from left to right. Okay? So one of the things I want you guys to do is figure out what equations do we need to have. This was just kind of give you an idea of the start of how we're going to get these. So this is V total. This is VR1, R3, R4, this guy's R5, R3, and R1, and the V total again. So take this home, look at it, and we'll talk about it again later. But, because we're still trying to solve the voltages for all these guys. Right now, all we have is this voltage. We should be able to use simultaneous equations to get these. Yeah, so I claim.
Well, we have 3 variables in each thing, so shouldn't we need 3 equations?
We need 3 equations, but we need to have the same equations or same variables in those equations.
So we need to come up with a 3rd equation.
Third or fourth. If we could, because we could get it to 4 variables. Because right now,
Can we just do like mini circles around the,
as long as it's a full loop.
and those could work for equation
Mhm.
12?
So we might end, I think we could do it with 3. Okay. Like I said, take this home, look at it. You can solve it using simultaneous equations. It's just a lot more complicated. But this is just kind of a good practice to figure out what do I need to get my simultaneous equations. Okay. I'll even let you guys go a minute or 2 early. Have a good day. Take your quizzes.